chapter 3. Let me fit it on the screen. Okay, that's good. All right. So there's a lot of topics here, but all we're going to talk about today is security models. And I remember this when I first did the CISSP is very interesting material I'd never heard of before that helped me understand how security evolved. And so here they are. These are the basic models. And the most essential ones here are Bell, LaPadula, Biba, and Clark-Wilson. And those helped me understand how we discovered what security was. We'll talk about these others also. So the basic concept is this. You have down and up. There's lower levels and higher levels. In secret things are higher levels of security. Unclassified things are lower levels of security. So no read up is the first obvious security property. The whole point is confidentiality. You don't want people to have top secret information if they are not cleared for top secret. So people that are only cleared for confidential should not be allowed to read top secret. That's the most obvious point of security, and this was the first model. You cannot read anything above your security clearance. No read up. That's called the simple security policy. And that's what the first model was, Bell-LaPadula model, and it does create confidentiality. All right, the problem is you can write up. Of course, you could write something and it could then move up and be classified. That would be all right. But that means a person at secret clearance could discover something which then goes up to top secret and passes beyond their clearance. That does not violate confidentiality. What it does, however, is it violates integrity. And so that's the issue. They first only thought of confidentiality. All they thought about security was keeping secrets. Then they discovered that that wasn't enough because top secret data cannot be written down to secret machines through a formal process of declassification. If you want to take top secret things and put them in a lower level, you have to go through a formal process to declassify them. I remember this is a big deal in Trump's first and second impeachment. So people with top secret clearance can read anything lower, and that does not violate confidentiality. All right. So that was the first model that just created confidentiality, but as we'll see, it made trouble because it didn't protect integrity. Anyway, the state machine model is what these are like, where you have the computer systems run in what's called discrete math, and they are technically state machines. You have a system with a certain state, and you just move from one state to another. So you have certain people accessing files, then another person accesses a file, you change the state. So you consider every possible interaction between the subject and objects, and if every possible state is secure, then the system is secure. This is the mathematical way you prove it. So the Bell-LaPadula model was developed for the Department of Defense, and it maintained confidentiality, which is all people thought about at that time for security. There's two rules, no read up and no write down. So the low privileged people cannot read the high privileged data, and the high privileged data cannot be moved down to a lower level without a formal process of lowering its classification. All right, so that maintains confidentiality, but it does not maintain integrity. Low privileged operatives can end up putting data that ends up high, and nothing prevents that. So when it actually implemented in a computer system, this did not achieve the goal of security. It has confidentiality, but this is how they discovered that confidentiality is not all you need to be secure. You also need integrity, which means the data is not being altered by unauthorized people. So there's a tranquility process and a weak tranquility that determines that just another way of describing how the system is going to maintain its security state as it is used. And there's lattice-based access control, where subjects and objects have a complicated arrangement like clearance, need to know, and role, and they have a least upper bound and a greatest lower bound of access. This is a much more complicated model. And the highest level of access, you have alpha, beta, and gamma. So you get some setup like this. This is one model. I've never seen anybody use this. Somebody must. But this is one model that's out there. Now, the second model after the Bell-LaPadula model was the Biba model, which was a response to that. Since the Bell-LaPadula model had a flaw that it did not protect integrity, they made the Biba model, which is the opposite. No read down and no write up. So you can't read, appropriate people at high levels cannot read data at lower levels, so they can't be misled by that, and it can't move up. And no write up means lower level data cannot move up. So this creates integrity, but not confidentiality. You allow read up so people at low levels can read all the data. So integrity, and this is how they discovered the arrangement, integrity and confidentiality are opposing goals. You can't have perfect integrity and perfect confidentiality at the same time. And as you probably know from Security Plus, there are three things you need: confidentiality, integrity, and availability, and they all oppose each other. So you can never have a perfect level of all three. Like in this room, we have a bunch of public machines. Anybody can use them. We don't even verify that you're a student or anything. That's high availability. In return, we have no confidentiality, there's no secrets, and we have no integrity. Anybody can put data on those machines. So you can have confidentiality, integrity, and availability, but they can't all be perfect, and you have to choose what's best in your situation. So the Clark-Wilson is the model, basically, we ended up with, essentially, where you have, well, it's one of the many that allow you to mix these two and hit in the middle. So this one here, you have subjects, access objects, the programs have limitations, and so there are well-formed transactions and separation of duties here. So you start with unconstrained data items, like data that comes from the user, and untrusted user input, and what you have to do is convert that into constrained data items, which is data which is now added to your system in a way that is in obedience to your security policy. And so you have well-formed transactions that maintain your integrity and makes an audit record. And you have separation of duties, so if one department collects money and another department issues payments, neither of them can perform purchase orders all alone. That's the idea. That's certainly the way at the companies I've worked at. Anything that involved sending money out had to be approved by two separate people to make sure no one person can easily steal the money. Anyway, these are some common issues, and I just mentioned it's kind of handy to remember it's alphabetical. These are the three main models that you talk about. The Bell was first, that gave you only confidentiality. Then BIBA was second, that gave you only integrity. And then you had Clark-Wilson, which is the one where you can have a reasonable mixture of these two, as we all came to understand that you cannot have perfect confidentiality and perfect integrity. You have to compromise between them. All right, so let's do a Kahoot about that one, which is here. All right, I'll wait a bit. People still coming in. All right. All right, so which model ensures confidentiality but not integrity? That's the Bell model. Good. All right, which model uses alpha, beta, gamma access? right, that's the lattice model. All right, which model has no read up? That's the Bell model, confidentiality. Low privileged people cannot read the high privileged data. All right, which model enforces no read down? Yeah, Joe, it's lattice. Lattice does alpha, beta, gamma. That's the BIBA model, the second one that gives you integrity. All right, good. All right. Bet. All right, let me stop this one.